The next piece of graphical analysis that we want to look at are identifying where graphs increase and decrease. Now, just to make sure we're on the same page, when we use the word increasing, it means that it rises, but more importantly, from left to right. Likewise, a decreasing function will fall from left to right. It's important that we all agree on that definition because obviously, if we switch it and maybe view it from right to left, what I may see as rises may be something someone else sees as falls. So we're going to treat this like we do slope. We work from left to right, so anything that is getting bigger y value wise from left to right is increasing, and things that decrease in y values from left to right will be called, decreasing. Now, to talk about kind of how this works, obviously I have this little graph here that does all these different things, so we can get our vocabulary right and kind of understand how we're going to do this without a picture. So to begin, I want to point out that this peak right here is a place where it changes, okay? Which means that from the initial spot to that little peak right there, that local min, this is a place where the graph is increasing. And I want to point out why I'm writing it here along the x-axis because when we identify where graphs do these things, it's a where question. So the answer are going to be intervals of x, right? How much of the x-axis over which the graph is increasing. Now, that means from about here to here, the graph is decreasing, okay? Because this is obviously moving upward. Now it's moving downward. After that, up to this little sharp corner there, again, that's now increasing again. So as you can see, graphs can both increase and decrease on any interval, but there is the option with some graphs that it also could just, be moving horizontally, right? In this case, we'll refer to that as constant. That's a much less common outcome, but at the end of the day, our job is to identify where graphs are either increasing, decreasing, or constant. Now, because we're going to do this without looking at a picture, we've got to come up with some sort of way of figuring out where these things are happening, right? To do it without seeing it. And so what we're going to focus in on is where these things change, right? Increasing and decreasing, and how do we know if it's increasing or decreasing on these intervals? Well, the first thing I want to highlight is that at these places, and I'll make dots right here, and right here, what we notice at those spots is that each and every one of these is a place that's a critical number. So that means that at each and every one of these places, we have places like this first two, right, this relative min and max, that are going to be places where the derivative equals 0. And here we have that sharp corner, and that's a place where the derivative is undefined. So the first thing I want to take away from this picture is that if I'm going to try and identify these intervals, I want to know where the critical numbers are because they break the graph up into places where it increases and decreases. Now, the second thing we want to notice is that when we're increasing, that's essentially just the idea that we're rising, right? We have a positive slope. Likewise, anywhere we're decreasing, we have a negative slope. And if we're constant, the slope is going to be 0. So if we look at things like, okay, slope is positive, and then over here, slope is negative, and over here, slope is positive, or even slope equals 0, those are the little things we can look at analytically to inform us about these graphs that we can't just look at. Okay, so if we put all this together, we can say, well, first off, let's figure out the critical numbers, right? Let's break the graph up into places where it may change. And then secondly, let's look at the slopes. When we have positive slopes, we're going up, negative slopes are going down, and 0 slopes, we're horizontal. And of course, since we're talking about the slopes of a graph, that means we'll be using the derivative. So our goal today is, of course, testing for increasing and decreasing analytically. And so based on the picture we just talked about, we're going to literally look for where the derivative is positive. We know that its graph is of the original function f is increasing. And where the graph's derivative is negative, then the original graph is decreasing. And anywhere the derivative equals 0, from more than one spot, we'll just say that's constant. Clearly, if its derivative equals 0 at one spot, that's just going to be a critical number like these two. We're talking about like an interval, okay? Now again, when we do this, it's important to remember that we're going to be using the derivative, right? And the derivative is going to inform us about the original graph of f. So we're going to be using sign charts to help us organize our thoughts. So we're going to be looking at a sign chart or the signs of the derivative, and that helps us analyze the function f. And it's important to make sure you keep that straight, right? We have this original function. We're going to make a new function, the derivative. We're going to analyze it. We're going to look at its signs, but its signs, remember, are the slopes of this original graph that we can't see. So make sure you keep it straight that, yes, there's two functions in front of us. One of them is the graph we're analyzing. The other is the tool, right, that we use to figure out what kind of slopes that graph has. Okay, so let's try an example. Here we're going to identify the intervals over which the graph f of x here is increasing or decreasing. So step number one, let's find our derivative, because we're going to figure out where those critical numbers are and as well find out what the signs are. Now by power rule, the derivative is going to be 12 minus 3x squared. And I'm going to set that equal to 0 right away. And I say that because this derivative here is a polynomial, so it doesn't have any non-differentiable points. So that means, it's going to work for all of them. So the only critical numbers are going to be where it equals 0. Now I'm also going to factor out, the common number here. In this case, it's going to be 3, so that's going to be 4 minus x squared. Now when I solve that for 0, clearly x squared needs to equal 4, telling me that the x values need to either be positive or negative 2. Okay, these are my critical numbers. Now what that tells me is that when I want to examine the signs of the first derivative and make my sign chart, the numbers that have to show up here are going to be those critical numbers. Now remember, this is a sign chart that's increasing in value. It's just like the x-axis is a number line, so we'll put those on there. And what we're going to do is we're going to select some value on this interval and some value here in between -2 and 2, and some number bigger than 2, and we're going to plug it into the derivative. Okay, remember in front of your face here, you're kind of looking at two different functions, but this sign chart, and that's why I've labeled it here, is about the signs of the first derivative. So when you're testing values to know if it's positive or negative, we plug it in here. And actually, I'll point out, when I actually plug stuff in, I like to go to the factored version if I can, because I don't care what the answer is. I only care if it produces a positive or negative result. So oftentimes, when you pick a number on the intervals, going to the factored version is an easy place to go. So let's try that out. Let's pick something easy like -3. Well, if I plug -3 in here, -3 squared is going to be a 9, right? 4 minus 9 is negative, and negative times some number 3 is going to give me a negative value. So what I know is that the derivative is negative on this interval. So the slopes of this graph are negative on that interval. Now another easy number to pick here in the middle would be 0. And again, if I plug 0 in here, that's going to be 3 times 4. That's a positive number. So that means that the derivative has positive numbers here, telling me that the graph of f has positive slopes there. Now my last number, I think another easy number is going to be 3, and when I plug that in here, I actually get the same result as -3. So again, on this interval, I get negative derivative values, and again, what that tells me is that the graph has negative slopes on that interval. Now, one thing to keep in mind, obviously, as you do this, right, is that these pluses or minuses, it doesn't matter what the y value is. We just care about whether it's positive or negative, because that's informing us about the slopes. Now, since I have these on here and ready to go, now what I can, of course, say is where this graph of f is increasing or decreasing. So I'm going to go ahead and label my increasing, and the graph of f will increase wherever it has that positive slope, which means that happens from -2 to 2. And as you notice, we definitely have to have the open intervals, right? At 2 and -2, the slopes are actually 0, so we don't include them as far as being increasing. Now for decreasing, we have the other areas, right? From -infinity all the way up to -2, and then we union also has negative slopes from 2 to positive infinity. So I can't see what this graph looks like, but by examining the intervals over what kind of slopes it has, I can tell where it's going up and down. Now let's try one more example, but this time with a little bit different style graph, so we can look at some different kind of outcomes. Now to find the derivative of this one, we're going to have to use the quotient rule. So for g prime, we're going to take the derivative of the top, which is going to be 4x, multiply that times the bottom, x minus 1, subtract the derivative of the bottom, which is 1, times the top, 2x squared, and then divide that by our quantity of the bottom squared. Now I know in the past we often don't really do much other than kind of lay this out, but because we're using this derivative to do stuff, we do want to simplify it. So if I can combine like terms and put all that stuff together on the top, we're going to get a positive 2x squared minus a 4x on top. And on the bottom, we're going to leave it alone. Okay, one thing I do want to point out, anytime you work with the quotient rule, really don't do anything with this bottom. Unless you can truly cancel out like a common x minus 1, don't expand it or anything, because, like you saw, we're going to plug numbers in and want to know what their signs are, and leaving it this way is actually helpful. Now, the first thing I should notice when I set this thing equal to 0, or looking for really any critical numbers, is that it does have a point that's undefined. Okay, so if I plug 1 into the derivative, it is undefined. But it's not a critical number. And the reason for that is not only does it make my derivative undefined, but it also makes the original graph undefined. So even though that's something we look at, because it doesn't exist in the graph, it's simply a vertical asymptote. Now that's going to be important to note. So I'm actually going to go off the side here and say that just as a note, x equals 1 is a vertical asymptote, because we're going to need that, but it's not a critical number. Okay, so we're not going to, have that be a place where any mins or maxes happen, but we do want to keep it in mind because vertical asymptotes are a place where you could change from increasing to decreasing. So we'll keep that in the back of our minds, but again, not a critical number because it doesn't exist in the graph. Now, if I'm solving a fraction for 0, it's only the numerator that I care about. Okay, so I only need to solve the top, and they both share a 2 and an x, so I can factor it this way, telling me right away when I look at the factored form that x equals 0 and positive 2 are my actual critical numbers. So when I make my sign chart for G prime, I definitely want to get my 0 and get my 2 on there because at critical numbers, right, we have possible places of changing the sign of G prime where the increasing and decreasing of G happen. But because we have that vertical asymptote, we also want to make sure we include that, okay? So even though it's not a critical number, it does need to show up on our sign chart because at vertical asymptotes, those are places the slopes can change from positive to negative, right? So we want to make sure we're checking both sides of it and not assuming that they all have the same thing. Okay, now again, as always, we're going to be taking any number in between here and plugging it into the derivative to look at the sign of it, to tell us about the slopes, to tell us about the increasing or decreasing of G. Now, I'll tell you right now, when I plug this in the fast, easy way, I'm actually still going to go right here because, again, I don't care what the answer is. I only care about whether it's positive or negative. And if you look at the denominator, whatever number that works out to be, you're squaring it. So in this case, with the derivative, the denominator is always a positive value. So honestly, the numerator alone, and this is the factored version of that, is the only thing that will play a role in whether or not I have a positive or negative value. So it's going to be real quick and easy just to evaluate it here. So for instance, if I choose for -1, when I put a -1 in here, that's going to make this part a negative and make this part a negative. And negative times negative tells me that this is going to be a place where the derivative has positive values, or the graph of G is increasing. Now, between 0 and 1, I'm going to choose just 1/2. So if I plug 1/2 in here, I'm going to get a positive here and a negative here. So positive times negative gives me a negative. And then if I choose, for instance, 1.5, like 1.5, this is still positive here, but this is still going to remain negative. So we still have another interval where we have a negative derivative. So the graph is decreasing there. And I'm just going to choose 3 here on the other side of 2, and plugging 3 into both of these produces a positive. And of course, if you have positive times positive, we get positive. So now that I made my sign chart, I can make my conclusions about G. So if I want to know where the graph of G is increasing, it's going to be where we have those positive slopes. So from negative infinity all the way up to 0, and everything after 2. Again, open intervals. And the places it decreases are going to be where it's negative. Now, it's important to remember that, yes, it goes minus, minus, but we have to write these as 2 separate intervals. Because at 1, we have a vertical asymptote. The graph doesn't exist there. So when I write down the intervals, I can't include that number. Okay, so even though they both share a negative and the graph is decreasing there, we have to break it up. So that means my decreasing is going to go from 0 up to 1, and then everything from 1 to 2.